How did humanity go from lashing reed mats to wooden posts in the Persian desert, to engineering carbon fiber blades that spin faster than the speed of sound at their tips? For 3,000 years, we have been obsessed with a single impossible task: capturing the invisible force of moving air and converting it into useful mechanical work. From the ancient panemone windmills of Sistan, which relied on nothing but raw air resistance to grind grain, to the mathematically optimized blade profiles of 2026 that extract energy from the atmosphere at efficiencies their inventors would have considered supernatural, this is the story of how we finally mastered the physics of lift over drag. The reed mat that the first Persian millwright lashed to a vertical post produced torque through brute friction with the wind. The carbon fiber blade that sweeps through the air above a modern offshore turbine produces lift through the same invisible aerodynamic principle that keeps a commercial aircraft aloft. And it does so at tip speeds that approach the velocity of sound, extracting energy from a fluid that cannot be seen, cannot be touched, and never stops moving. How does a simple wooden blade become an advanced system capable of powering entire cities? The answer lies in 3,000 years of engineering breakthroughs in structural pitch control and mechanical torque. A slow accumulation of physical understanding that transformed a curiosity of the ancient world into the most rapidly expanding energy technology on Earth. We examine the complex physics that allows us to harvest global atmospheric energy, tracing the evolution from the first Persian millwrights who harnessed wind through drag alone, to the engineers who discovered that a curved surface moving through air generates a force perpendicular to the flow, a force so much more powerful than simple air resistance that it changed the fundamental design of every wind machine built afterward. That discovery, made incrementally across centuries of empirical experiment and formalized by aerodynamicists in the early 20th century, is the reason that modern wind turbines can extract energy from winds that would have been too weak to power the oldest windmills. 3,000 years ago, this story began with a vertical sail spinning in a Persian desert, grinding grain through nothing but the push of the wind against its face. Today, it has become the most sophisticated application of aerodynamic engineering outside of aerospace. Blades that generate lift, not push, converting the invisible currents of the atmosphere into the electricity that powers the modern world. Stop thinking of wind turbines as rotating blades, and start seeing them as the apex of aerodynamic evolution. From ancient sails to the high-speed blade profiles that have made wind the fastest-growing energy source in 2026, this is the 3,000-year journey from friction-based machines to elite aerodynamic energy converters, and the story of how humanity perfected the transition from simple drag to sophisticated lift. The windmills of Sistan, in the region of ancient Persia now spanning eastern Iran and western Afghanistan, are the oldest wind-powered machines in the historical record. They appear in Arabic manuscripts from the 9th century AD, but the technology they describe, vertical axis windmills, using woven reed or wooden sails to capture wind through air resistance, is almost certainly older, with estimates ranging from the 7th century BC to the early Common Era. The panemone design is straightforward to the point of being obvious in retrospect: a vertical shaft, mounted in bearings of stone or wood, with a set of flat or slightly curved sails radiating outward from it like the arms of a wheel lying on its side. The wind pushes against the sails on one side of the shaft. The opposite sails are shielded by a wall or by their own orientation, and the differential force rotates the shaft. The rotation is used directly to drive a millstone, grinding grain into flour. The engineering is elegant within its constraints. Those constraints are severe. The fundamental limitation of the panemone design is that it extracts energy from the wind exclusively through drag, the force that a fluid exerts on a body moving through it, or equivalently, the force that moving air exerts on a stationary object facing into the flow. The drag force on a flat sail is proportional to the square of the wind speed and to the area of the sail, but it is fundamentally bounded by the momentum of the air striking the sail. No drag-based machine can extract more than a fraction of the kinetic energy in the wind passing through its swept area, and in practice, drag machines operate well below that theoretical ceiling. The Betz limit, the theoretical maximum efficiency of any wind energy extraction device, is approximately 59% of the kinetic energy in the wind. Drag-based machines like the panemone achieve efficiencies in the range of 10 to 15%. The gap between those numbers represents the potential of a different physical principle, one that the Persian millwrights had no systematic way to discover. The geographic migration of windmill technology from Sistan westward into the Islamic world, and then into medieval Europe, followed trade routes and the movement of scholars and craftsmen across the caliphate. By the 12th century, windmills were operating in the coastal lowlands of northwestern Europe, in Flanders, in England, in Normandy, adapted to climates and wind patterns very different from the Sistan Plateau. The European environment, with its variable winds and overcast skies, favored a different design, a horizontal axis machine, with sails mounted on a shaft pointing into the wind, rather than rotating in a horizontal plane. The transition from vertical to horizontal axis was not simply a stylistic variation. It was the first step toward an entirely different aerodynamic regime. The post mill, the earliest form of European horizontal axis windmill, mounted its entire operating machinery on a single large post, allowing the whole body of the mill to be rotated to face into the wind. The sails extended from a horizontal shaft at the front of the mill, their plane perpendicular to the wind direction, and the rotation of that shaft drove the millstones through a system of wooden gears. The design required the miller to manually rotate the entire structure as the wind direction changed, a laborious operation that limited the mill's practical productivity and drove the development of the cap mill and the smock mill, in which only the cap holding the sail shaft rotated, leaving the main structure fixed. These were practical engineering improvements, but they concealed a more fundamental development happening in the shape of the sails themselves. European millwrights, through generations of empirical observation and competitive refinement, began to notice that a twisted, cambered sail, one that was not flat but slightly curved, and whose angle to the wind varied along its length, performed better than a simple flat canvas. They could not explain why. They did not have the vocabulary of aerodynamics or the mathematics of fluid mechanics. They had the observation that a certain shape of sail, at a certain angle to the wind, turned the shaft faster and with more force than any flat sail of the same area. What they had discovered, without knowing it, was the principle of aerodynamic lift. A cambered surface moving through a fluid generates a pressure difference between its two faces. Lower pressure on the convex side, higher pressure on the concave side, and that pressure difference produces a force perpendicular to the direction of motion. That force is lift. It is the same force that allows an aircraft wing to support the weight of the aircraft. And it is dramatically more powerful, per unit of blade area and wind speed, than the drag force that the Persian panemone relied on. The Dutch smock mill of the 17th and 18th centuries represented the most refined empirical expression of this principle before the age of scientific aerodynamics. Dutch millwrights, serving a country that depended on windmill power for drainage, grain milling, and industrial processing, developed sail geometries and twist distributions that modern analysis confirms were close to optimal for the available materials and construction methods. They achieved this through craft knowledge passed between generations, through competitive observation of what worked, and through the pragmatic engineering culture of a society for which windmill performance was an economic survival question. The transition from drag to lift had been made, incompletely and without theoretical understanding, but made nonetheless. The formal science of aerodynamics arrived in the late 19th and early 20th centuries, and with it came the ability to design wind machine blades from first principles rather than from accumulated craft knowledge. The same theoretical foundations that explained how aircraft wings generated lift, the work of Kuda, Joukowsky, Prandtl, and their contemporaries, could be applied directly to the design of wind turbine blades, which are, in aerodynamic terms, rotating wings. The blade element momentum theory, developed in the early 20th century, allowed engineers to calculate the optimal chord width, twist angle, and airfoil section at every point along a blade's length, maximizing the extraction of energy from the wind across the full range of operating conditions. Albert Betz published his theoretical limit for wind energy extraction in 1919. No wind energy device, regardless of its design, can extract more than 1627, approximately 59.3%, of the kinetic energy in the wind passing through its swept area. This is not a limit imposed by engineering imperfection, but by the fundamental physics of momentum conservation. Some kinetic energy must remain in the wind downstream of the turbine, or the wind would stop flowing through the rotor entirely. The Betz limit established the ceiling against which all subsequent blade designs would be measured. The challenge was to approach that ceiling as closely as possible, with real materials, in real atmospheric conditions, at practical costs. The materials available to wind machine designers expanded dramatically through the 20th century. Steel replaced wood for structural components, allowing larger blades with thinner profiles and more precise geometry. Fiberglass composite construction, adopted from the boat-building industry in the 1970s and 1980s, allowed blade manufacturers to produce complex, precisely shaped aerodynamic surfaces that would have been impossible in wood or steel. The composite blade could be optimized for both aerodynamic performance and structural integrity, its fiber orientation tailored to resist the bending loads imposed by lift and the fatigue loads imposed by millions of rotational cycles over a 20-year operational life. The tip speed of a modern wind turbine blade is a number that requires a moment to appreciate. At full power, the tip of a blade on a large turbine moves at speeds of 80 to 90 meters per second, roughly 300 kilometers per hour, or nearly 1/4 of the speed of sound. At that velocity, the aerodynamic forces on the blade tip are enormous, and the structural demands on the material are correspondingly severe. A composite blade operating at tip speeds, approaching transonic conditions, is no longer simply a scaled-up version of a Dutch mill sail. It is an aerospace structure, and it is designed using the same analytical tools and manufacturing standards as an aircraft component. The fixed-pitch blade of early wind turbines operated at a single angle of attack regardless of wind speed. This simplicity had an obvious cost. A blade optimized for one wind speed performs suboptimally at every other wind speed, and the range of wind speeds over which a turbine must operate, from the cut-in speed at which the rotor begins turning to the cut-out speed at which the turbine must shut down to prevent structural damage, spans more than an order of magnitude. The solution was active pitch control, a mechanism, typically hydraulic or electric, capable of rotating each blade around its own longitudinal axis to change its angle of attack in response to current wind conditions. A blade pitched to a high angle of attack in low winds extracts maximum energy from the available flow. The same blade, pitched to a lower angle of attack as wind speed increases, limits the torque transmitted to the generator and prevents the rotor from accelerating beyond its design speed. At extreme wind speeds, the blade is feathered, rotated so that its chord line aligns with the wind direction, generating neither lift nor drag, and allowing the rotor to stop safely without structural overload. The engineering of the pitch control system, the bearing that allows a multi-ton blade to rotate around its axis while under aerodynamic and centrifugal loading, the actuator that drives that rotation with sufficient speed and force, the control algorithm that determines the correct pitch angle at every moment, represents a significant fraction of the total engineering complexity of a modern wind turbine. Modern pitch control systems respond to wind conditions measured by nacelle-mounted anemometers, and increasingly by LiDAR systems that scan the wind field ahead of the rotor, providing a preview of incoming turbulence that allows the control system to begin adjusting pitch before the turbulence arrives at the blade. The LiDAR-assisted control system effectively gives the turbine a few seconds of advance warning of changing conditions, enough time to optimize the blade pitch for the incoming flow rather than reacting to it after the fact. Artificial intelligence has entered wind turbine control at multiple levels. Machine learning algorithms trained on years of operational data can predict the development of fatigue damage in specific blade locations, schedule maintenance before failure occurs, and optimize the operation of entire wind farms, adjusting the yaw angle and power output of individual turbines to reduce the wake interference between adjacent machines and increase the total energy output of the farm as a system rather than as a collection of independent turbines. The wind turbine blade of 2026 bears as little physical resemblance to the reed mat of the Sistan panemone as a modern aircraft wing bears to the kite that Benjamin Franklin flew in a thunderstorm. The longest blades currently in service exceed 100 meters from root to tip, longer than the wingspan of the largest commercial aircraft. They are fabricated from carbon fiber reinforced polymer, a material that combines the stiffness required to maintain the blade's aerodynamic shape under load with the fatigue resistance required to survive 20 years of continuous cyclic loading, and the low density required to keep the blade's mass within the limits that the hub, main bearing, and tower structure can support. Carbon nanotube reinforcement, being evaluated in prototype blades as of 2026, offers the prospect of further increasing the specific stiffness of blade materials, allowing even longer blades with thinner, more aerodynamically efficient profiles. The relationship between blade length and energy output is not linear but approximately cubic with respect to wind speed and quadratic with respect to blade radius. Doubling the blade length increases the swept area by a factor of 4, extracting 4 times the energy from the same wind speed. This scaling relationship is the fundamental driver of the industry's relentless pursuit of larger turbines. Floating offshore wind turbines, platforms moored in water depths that fixed bottom foundations cannot reach, carrying turbines above the surface, extend the geographic range of wind energy harvesting to the deep water ocean areas where wind resources are strongest and most consistent. The engineering of a floating wind turbine platform must simultaneously satisfy the aerodynamic requirements of the turbine, the hydrodynamic requirements of the floating structure, and the mooring requirements of the anchoring system, while maintaining the precise vertical orientation that wind turbine rotors require. Airborne wind energy systems, tethered kites or aircraft that fly in figure-8 patterns at altitudes where wind speeds are higher and more consistent than at surface level, transmitting power to the ground through the tether. remain at the demonstration stage but represent a fundamentally different approach to the altitude limitation that constrains conventional towers. 3,000 years of trial and error, from the empirical craft of the Persian millwright to the computational fluid dynamics of the modern blade designer, has transformed the invisible air into the most reliable and rapidly expanding energy source available to civilization. The wind that blew across the Sistan plateau and turned the first panemone still blows. The physics that governed its interaction with a reed mat still governs its interaction with a carbon fiber blade 100 meters long. What changed across 3,000 years is the depth of our understanding of that physics, and the precision with which we have learned to exploit it.